Hello students, here I am with my second lesson. Today I am going to teach you that is the control of separately excited or shunt DC motor using controlled half-wave converter. So this is a circuit of the controlled half-wave converter. Here is the AC supply. As you can see, it can be fed through a single phase transformer. Here the transformer is not shown, but it has been depicted as an AC source. This is the thyristor, the control switch, and in the full wave converter you have seen that we had used 4 thyristors, but here in case of half wave converter, controlled half wave converter, we are using single thyristor. There is this freewheeling diode. What is its purpose? I will explain it to you later. And this is the RLE load, which depicts the the DC machine. I told you last day also that is the DC machine can be depicted by an RLE load. And this is my output current, this is my supply current, this is my supply voltage, and this is my output voltage. Right. And this E here represents the back EMF developed in the machine, and this R and L are the resistance and the inductance of the motor windings. So this is a circuit diagram as I have explained to you, and now let us come to the most important part, that is the waveforms. So as you can see, this is the supply voltage, the pure AC sinusoidal voltage. This is the alpha. Alpha is our triggering angle. We will be triggering this thyristor T at every cycle at alpha. This is a half wave converter. That is why we will not be triggering this thyristor in both the half cycles. We will be triggering it in the positive half cycle, and next we will be triggering it in the positive half cycles of the next time period, right? So this is my time period. T, right? This is my time period T. So this is my output voltage waveform. We can see that as we trigger this thyristor T at alpha, when the thyristor T is triggered, so this becomes short circuited. So the input and the output wave. So this point, supposing we name this point as P, and supposing we name this point as Q. So these 2 points become the same, short circuited, shorted. So basically the input voltage waveform comes across the output voltage waveform. So as we have triggered at alpha, so after that see the output voltage waveform follows the input voltage waveform. Now because of this high inductance in the output circuit, this inductance is much, that is L is very greater than R. Because of this high inductance in the output circuit, this output voltage waveform should have gone negative. That is, the output voltage waveform should have followed this, right? As we have explained in the last video, that because of the output voltage waveform, we can see the output current conducts beyond pi also, and because of this output voltage waveform should have become negative beyond pi, but it didn't become negative and it stopped at 0. It is because of this freewheeling diode. We'll come to it later, just a few minutes later. So the output voltage here is from alpha to pi. We can see after that in the negative half cycle there is no triggering, and again at 2 pi plus alpha we again trigger this thyristor T, and it again conducts for alpha to pi. So this conduction time is pi minus alpha. The next is the output current waveform. So we can see, because see, as we trigger this thyristor, so this supply from the AC supply, this current IS flows, the freewheeling diode does not flow. As we trigger this thyristor at alpha, this IS flows through I0, and it follows this path. Okay, it follows this path. So it follows and it charges the output, that is this L, right? It charges up, and at certain instant the current again starts falling. It's falling because it starts falling as the polarity of this inductor, supposing means when it starts charging, its polarity is plus minus, and when this current decays, the current starts to decay when the polarity of this inductor becomes negative. That is, this becomes this polarity then becomes minus, and this polarity then becomes plus. That is, it inverts the polarity. Then this current starts discharging. Now as it starts to discharge, now see, there is only one thyristor, so the current starts discharging. Now the direction of the current can only be this, as this is a unidirectional device. So the direction of current cannot change. The polarity of the inductor changes, so current still conducting in this direction. So what happens? So this output voltage now should have followed the input voltage continuously, but what happens at the value of pi, as the input becomes negative, right? So this thyristor becomes reverse biased. But as the polarity of the inductor is reversed, so therefore what happens, this forward bias is this freewheeling diode. Now as this freewheeling diode is forward biased, so now the output current continues to flow in this path. This is the main mechanism. So the current charges up, and so the current rises up and then again decays till 2 pi plus alpha, and then again starts rising as and when this thyristor T is triggered. But this such a long value of the decaying period is a bit abnormal, as but we have to show this operation in the continuous conduction mode, and therefore I had shown that this current does not become discontinuous. So this is my I0 and this is my I average. I have considered it to be a constant DC current. Now this is a freewheeling diode. Now this freewheeling diode starts conducting from pi means as the voltage becomes negative. I told you previously, as the voltage becomes negative, so this thyristor gets reverse biased, but as the polarity of this inductor has already changed, so this becomes forward biased, and here at pi this is negative, so this also so this becomes reverse biased, this is positive, so this becomes forward biased at that time, and this freewheeling diode starts conducting from pi. So we can see this is IFWD. From pi it has started to conduct and will conduct till the thyristor T is again triggered. Now if it was discontinuous conduction mode, then this freewheeling current could have decayed to 0 at any instant between pi and this 2 pi plus alpha, but because we have considered continuous conduction mode, and therefore I had shown this to be continuous current. This is only the freewheeling diode, which is freewheeling diode current, which is just a portion of this I0. Now this is cancelled, right? And this is the supply. That is the see, from I0, if you separate this IFWD, what is left is IS. That is the supply current. That is the current passing through the IS. This much of current flows from alpha to pi. That is when this supply is supplying power to the load. That is from alpha to pi. Beyond pi, what happens? It is that energy stored in this inductor that is supplying this current, that is dissipated in this closed circuit. That is, in this resistor it will be dissipated, and it will be dissipated gradually, and the current gradually decays and falls to gradually decays. So this is the supply current. Now let us come to this. Now this is the average voltage from the waveform. It is quite understandable. That is the V0, that is the output voltage is 1 by 2 pi alpha 2 pi Vm sin omega t, as we have discussed earlier also. So this is the known result. You must know this. But now, as from here we can see, for any value of alpha between 0 to 180, the output voltage does not go negative. So therefore it's a first quadrant operation is only possible in this kind of half wave converter, unlike in full wave converter where two quadrant operation is possible. So the function of the freewheeling diode helps to keep the input power factor better and to keep the load current continuous. So for the load current to be continuous, the freewheeling diode has a role. So without the freewheeling diode, there is a high probability that during the that beyond pi the current will decay to zero. That will be a discontinuous conduction mode. Now the entire calculation is very much, this is a very much known result, the result for speed, and I have just replacing Ia by T by K phi. I have drawn a relation between speed and torque, and here I have to replace this value of V0 which we have derived here. V0 is Vm by 2 pi 1 plus cos alpha, so we have put here. So this is my speed torque relation. This is my no load speed at various value of alpha. So with different values of alpha with the variation of t, we get the speed versus torque characteristic, and this is the nature of the speed versus torque characteristic. We see for first for alpha is equals to 0, alpha is equals to 30, alpha is equals to 90, we get different curves, and this is for alpha is equals to 180 we get at no load. So at alpha is equal to 180, what happens? See, this is torque is 0, so this term is cancelled, and V0 at alpha is equal to 180 becomes 0. See, for alpha is equal to 180, this becomes minus 1, so 1 minus 1 is 0, so V0 becomes 0. So at alpha is equal to 180, the no load speed becomes 0, and it gradually decays to the negative value, so with increasing the torque. So this is the motoring region, and this is the reverse regenerative braking region. As we know, there is the first quadrant offers the forward motoring region, and the fourth quadrant the reverse braking region. This is the reverse regenerative braking region. Okay, so this completes our analysis of the control of separately excited DC motor using controlled half-wave converter. The important points here is the circuit diagram, the waveforms, the deduction of this output voltage, the quadrant operation, function of the freewheeling diode, and this deduction, this is relation, and this ultimately what is our main intention is to derive the speed versus torque characteristic. Okay, thank you.